How we doing? Everyone's okay? You doing okay? Good. We can all hear? The camera can hear? Awesome. I did cut a lot of the hardcore chemistry out of this because I thought people wouldn't want to hear that. So, also, I'm really hoping that this is over in like a reasonable amount of time so there can be a significant time for Q&A after, because this is a complex topic and it's hard to narrow it down into like a simple one-pronged story. So I did my best to do that, but I anticipate that I will have left stuff out, so feel free to just assault me with questions afterwards. Let's go. All right, so let's begin. What are we going to do about the White Walkers? This is the conundrum, okay? So we have this army of ice zombies that live up here in the north. And they're slowly migrating down this way towards the wall to make it into the north of Westeros. And at first, there's only like a very, very small subset of people that even believe in the White Walkers, right? Like this is like a children's story. This is a myth. Like, these aren't real. We don't have White Walkers. What are you talking about? And then slowly the community, especially in the north that's being impacted by this the most, starts to be like, yeah, we need to worry about these guys. We need to reinforce the wall. But meanwhile, down here south of the neck, there's these economically prosperous lands of the Seven Kingdoms that are going to ignore the problem, pretend the problem doesn't exist. They're like, well, the North can deal with it. We're fine down here. We're going to keep going on with the status quo. Until, what's his face? I don't remember his name. Actually brings like an ice zombie down to them. Well, I don't remember what the guy's name is. Someone knows. Someone who's watched the show. It's all right. It doesn't matter. And then they're all, oh, this problem is real. Well, now let's debate over who's going to do something about the problem. Because it's not to any of our individual advantages to do something about the White Walkers. It's best for us if someone else does something about the White Walkers. But at the end of the day, for the common good of all of Westeros, we need to just bite the bullet and do something before they come in and overwhelm the entire Seven Kingdoms. That's the end of my talk. No, I'm kidding. All right. So, tackling climate change. Isn't this painting lovely? This was on the cover page of the recent IPCC report. I think it's really great. Anyway, so I'm going to break, my talk is in like 3 chunks. Chunk number 1, sections, for those of us who use real language. So the first section of the talk is evidence that climate change is the White Walkers, if you didn't pick up on the metaphor, is real. There is evidence for this. It's pretty compelling at this point. I'm not going to present all of it. The IPCC report, I don't know if anyone's read it. I sure haven't. It's 1,800 pages long. Yeah. So we'll talk about that. I'm going to then break down the overall problem into a couple individual problems by economic sector, and then show a few solutions that might come in handy in those various economic sectors. And then at the end, we'll tally it up with what all of us can do towards solving this. So that keeps you straight in your mind. Okay, cool. So the planet is warming up. This is pretty indisputable at this point. Like, even just in your lifetime, you have probably noticed the planet is warming up. Like on the right side of the slide, look, I can use the shadow of the stick. That's clever. Yes, so these are the 20 hottest years on record. And man, would it have been convenient to just say the 20 hottest years on record are the past 20 years. But unfortunately, that is not true because 1998 was really hot. But other than that, the rest of it is in the past 20 years. Consistent. People like to say, oh, well, that's just the El Nino year effect. You hear that all the time. And the El Nino year effect is a real thing. It's complicated. It has to do with ocean currents in the Pacific Ocean and all sorts of stuff. And whenever this happens every like 5-ish years, there is a hotter than normal weather phenomenon on the planet. And indeed, The years highlighted in red are El Nino years, so they're going to be the hotter years. But I mean, there's also the opposite of the El Nino year effect, and 2020 and 2021, we're currently in a La Nina year cycle where it should be colder than normal. We're not on track for that right now. So this has nothing to do with that effect. In fact, this is actually an animation of the data on here, if it will play. Will it play? If I go over here, will it play? There we go, yes. So this is data. We're in the 1800s. We're plotting colder than normal on blue, hotter than normal is on the red end of the spectrum. Here's the World War II we're at right now. Good? Now the boomers are alive. We're still going. It's the 70s. It's the 80s. It's the I'm alive. Okay, and we're going, and here is this year, and now it's the simulation based on the data. And we're going, and here's 2050, here's 2060, I might be retired now, it's 2070, it's 2080, it speaks for itself. Like, I don't really need to say much about that. I don't think. Like, you can just intuitively interpret this, unless you happen to live in the middle of the Atlantic Ocean, or in that specific corner of Antarctica. It's gonna be warmer. And it's not a lot warmer. Like, this is saying it's on average going to be about 2.5 degrees Celsius warmer, which doesn't seem like 2.5 degrees Celsius is like 5 or 6 degrees Fahrenheit warmer on average. The problem is that most of the world is covered in ocean, and the ocean doesn't really get much hotter or colder ever. So the average temperature going up by about 5 degrees Celsius means the land average temperature is going up by much more than, we'll say like 10-ish degrees Fahrenheit. 10 degrees Fahrenheit is a lot. That's the difference between snowing and not snowing. That's the difference between I can mow my lawn today and I'll wait until tomorrow because it's gonna be sweat-tastic, right? That's the difference between ice caps and no ice caps. It's a big deal. Where else have we seen this effect? I can get my mouse back over here. We've seen this effect in storms. It's relatively hard to like quantify. Storms are bigger and more common, and so the way that a lot of agencies do it is by the frequency of billion-dollar weather events. So these are weather events that cost, this is just in the US, the government $1 billion or more to fix, essentially. And this is accounting for inflation, by the way, because from 1980 to 2020 there was significant inflation difference. So this is accounting for that. And here's another graph that basically speaks for itself. 2021 looks not as bad, but we're only halfway through 2021, so hang tight. It can come back up as well. Basically, this happens because, as I've abbreviated up here, more heat equals more energy equals more and stronger storms. Is that an approximation? Yes, but it works very well, especially for like rain-based storms. If you have a hurricane or something like that, they feed off of the warm energy of especially tropical waters and just absolutely dump that on places on the coast. Like we've all seen the recent hurricanes. Again, it seems like every other year it's like this is the storm of the century. Yeah, that's what you said last year. Yeah. This is for real. This is detectable. This is measurable. We can see this. Oh, by the way, I have all of my citations down here on the bottom of the screen throughout the entire presentation. So if you want to like quickly snag a photo or something and look this up for yourself, I've got it. Also, if you can't find it, ask me. I got your back. Okay. Sea level rising. This is one you always hear about. Here's the actual graph of sea level rising. We don't have quite as much data on sea level rising. It's also hard to measure sea level because the sea likes to, move with time, right? Yeah. But this is our graph. So the black line on here, this is measurements via satellite. The blue, red, and purple, these are models. So the blue line down here, this is modeling additional water that's being added to the oceans. This is almost entirely from ice cap melting. So the North Pole and the South Pole melting. The red line down here is from thermal expansion of water. So you may not know this, but water actually expands and contracts a little bit as it heats up or cools down. The same way that like your heater in your house expands. When you turn on the heat for the first time, or like turn on the hot water and you hear the pipe going like click, 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 click in the wall as it expands. Seawater does that too. So this is a double whammy with sea level rising because A, there's literally more water, and B, the water is taking up more space. And if you take the blue line and add it to the red line, you get the purple line. That's all the purple line is them added together. And I feel like the model pretty compellingly lines up with the actual data. The purple trace is on top of the black trace. So according to this model, coupled with the climate models from IPCC, we should expect about 3 to 6-ish feet higher sea level by 2100. 2100 is usually the year where the model ends because it's the end of the century. Which again might not sound like that much unless you live in a coastal city. Like 6 feet higher sea level is the difference between the Manhattan subway being flooded and not. We'll take climate change seriously when the New Yorkers can't get to work in the morning. That's when it's gonna happen, yeah. The more serious thing for me though is the bottom bullet point on here, that it's really hard to estimate exactly where people live globally, but the low end is about 2% and the high end is about 10% of the global population is likely to be displaced out of their homes and places of business by 2100 just by sea level rise alone. Just because it's going to be flooded. There isn't land there anymore. This is including islands, particularly in the South Pacific, that are going to be just gone, because there'll be sandbars now. But also a lot of the world's biggest cities are just right on coastlines because it's convenient for shipping and trade and stuff. So 10% of the population is, what do we have, 7 billion right now? So that's 700 million people. So that's about twice the population of the United States is gonna be displaced from houses by 2100. And that's on the current model. That's the average of the current model. So we might be a little bit lower than that. We might be a little bit higher than that, but it's not going to be zero, let's put it that way. I'm sorry this is really depressing. I apologize for that. Okay. Normally I'm trying to be as peppy as possible. Where are the White Walkers? Anyway, cool. Let's talk about the greenhouse effect. What is the greenhouse effect? So this is a thing you have all experienced before if you have ever been in a car in Ohio in the summertime, which is probably everyone in the room, right? If it's sunny outside, you park your car over there, because that's where I park my car. You probably park your car over there if you're a student. And it's nice and air conditioned in your car, and then you go do work and school, and you go back to your car, and it's 80 degrees out here, but it's 110 degrees in your car, because the sun light goes through the windows, turns into thermal infrared energy, which can't go back through the windows and gets trapped in your car. So planets also have the greenhouse effect, which is good, otherwise it'd be very cold on Earth. The most extreme planetary greenhouse effect is between Mercury and Venus, actually, which is why I'm highlighting it here. This is not drawn to scale, by the way. If the sun were this big, Mercury would be like in Worley Hall, if it's to scale. Just so we're all clear, but that's okay. Worley Hall is over there for visitors to campus. Okay. So Mercury lives closer to the sun than Venus by quite a fair margin, actually. Mercury's average high temperature is a really delightful spring break, 800 degrees Fahrenheit. And its low temperature swings way down the other end when it's nighttime on Mercury, versus Venus is pretty constantly around 900 degrees Fahrenheit, even better spring break temperature. Because Venus has an atmosphere made out of greenhouse gases. So the heat from the sun hits the planet and then can't escape. It stays on Venus. So Venus is actually hotter than Mercury, even though it's farther from the sun. Conveniently, we live even farther from the sun. But the same effect holds true on Earth. We have heat trapped on our planet because we have gases in the atmosphere that trap some of that heat on Earth like a blanket. The problem is one blanket is comfortable, but like 6 blankets is uncomfortable. That's the opposite of comfortable. Champion. Okay, yes. Good. Carbon dioxide is a greenhouse gas. We're going to just accept this to be true for the purposes of this lecture. If you want to go into the mechanics of how that works, we can do that. It has to do with vibrational frequencies and changes in the dipole moment as the molecule stretches. We can go nuts. It's fun. We can do it, but we'll do it later. It's fine. We'll just accept that carbon dioxide is a greenhouse. There's other greenhouse gases that are common as well. For the purposes of this presentation and for the purposes of the IPCC report, they convert everything to equivalents of carbon dioxide. So we're just pretending that carbon dioxide is the only greenhouse gas in the atmosphere, and for other greenhouse gases, we just consider that to be a lot of carbon dioxide. So it's converting it all into that. It's fine. Anyway, so the plot, these are actually the same plot, and I've just zoomed way in on the time axis on this one. So this one goes from like the Rolling Stones to the beginning of next century. And this one goes from way into the future to as far back as we have a reliable record. This actually comes from ice core data. So this is I should say what this is. This is a plot of carbon dioxide that is in the atmosphere, going all the way back to the year, it goes slightly farther than 800,000. It goes to like 801,000 something BC. And they do this by making these holes in the ice in Antarctica, or in the Arctic, but this one's from Antarctica. And they bore a really, really, really deep hole. So the thing about Antarctica is it's cold. And the ice never melts. So if you dig really, really, really deep, that ice has been there for 800,000 years. So if you dig really, really deep, and you know how much carbon dioxide dissolves in ice, you measure the amount of carbon dioxide in that ice way down there, and you get this graph of carbon dioxide versus time. And this is a well-established process in the geology community. I 95% understand how it's done, but I'm not a geologist, so I would have to defer to an actual geologist for more details on that. But moral of the story, as far back as we can possibly measure, the concentration of carbon dioxide in the atmosphere has fluctuated a lot between about 200 and about 300 parts per million, which is just a concentration unit. You can convert parts per million to molarity if you want. We're not going to, but you can. All right? Currently, we're sitting at 417. So that's already like at least 50%, if not double, what it ever has been in certainly the history of humans on Earth. Like we're like almost to dinosaurs on this plot here. Not quite. Dr. Mathis? No, not quite. But old-timey animals that don't exist anymore on Earth. Yes, I'm not an animal biologist. Fun fact. Moral of the story, here we are at 417 ppm. And now we're going to jump over here to the zoomed in version because this just looks like a vertical line at this point because this axis is so long that you can't really tell what's going on. So here, this green line, this is this green line here. Here's 417. The low end projection for where we'll wind up with carbon dioxide in the atmosphere if we absolutely just like stopped today, like all CO2 emitting things, as quickly as we possibly could, is going to just asymptote at around like 550 ppm. And the relatively worst case scenario, first of all, has no end because we can emit as much carbon dioxide as we want, but it's somewhere in the ballpark of 900 ppm by 2100. This is a good time to remind you that 200 to 300 has been the norm for something on the order of 1 million years on Earth. Humans have not lived on Earth the last time we had sustained carbon dioxide or just greenhouse gas in general at these levels. So everything from here is just models, but none of it's good. So, great. Is this okay? Because understanding that, assuming that this is true, thus connects to like the entire rest of the presentation. So if there's a heckler, let's go right now. Okay, we're good. I only have one slide on this because this is kind of like a tangential rabbit hole, but CO2 concentration going up also leads to this phenomenon called ocean acidification. This happens because when carbon dioxide dissolves in water, it will automatically turn into carbonic acid, which is the acid that you'll find in like my favorite beverage of champions over here. And it's, you know, acidic. So as CO2 in the atmosphere goes up, CO2 in the oceans go up, and so the acidity of the oceans goes up. And we've measured this as well. So the red curve on here is CO2 in the atmosphere from 1958 to today, or just before today. That's fine. I love the name of this study, Aloha, because it's in Hawaii. So smart. I love it. Anyway, the green line on here is them measuring the concentration of CO2 dissolved in the water as a gas that hasn't turned to carbonic acid yet. It fluctuates a lot because the ocean is turbulent and complicated, but it more or less tracks with the atmosphere in red. And then in blue here is the ocean pH. And if you remember from school, whenever you learned about pH, low pH means acid, high pH means opposite of acid, which is base. So we have very, very low pH, we're getting more acidic. And we've gone down from about 8.15 to about 8.05 in the past 50 years or so, which doesn't sound like a lot, except the pH is on what's called a logarithmic scale, which I also don't really want to get into how that works right now, but I've gone ahead and converted them into concentration units. So we've gone from 7.1 nanomolar, so 10 to the minus 9 molar. These are a lot of my students over here, that's why I keep gesturing to them, to 8.9 now. So that's about a 25% increase in the acidity of the ocean in, what is that, 60-something, 63 years? So this is bad for things like, you know, shellfish that have to use minerals from the water to build their shells, and they can't because the water is too acidic. Like you may have heard of like the bleaching of the Great Barrier Reef in Australia is losing its color because they can't fix the color compounds anymore, so corals are on the decline. And this is going to continue as carbon dioxide continues to go up. This is the last slide on this topic, but we can talk about this topic a little bit later also. So this is a tangent that I went off on. Okay, so essentially, moving into the second part of the presentation now. So the biggest problem for the common, we're switching back to humans, I'm sorry, shellfish. The biggest problem for the common good of humankind is, so the adverse effects of climate change are going to be felt the most, the strongest, by people in developing countries who don't have the resources to adapt to this. Like, if the New York subway floods, we'll just install pumps, and New York will be fine. But if you don't have the resources to install pumps, you have to move. The awesome caveat to this is that, generally speaking, the people who are in the developing countries that do not have the resources to adapt are the people who contributed to the problem the least in the first place. So we have we being like those with money compared to, like, I'm not saying I'm rich, but compared to other places on Earth, have a moral responsibility to do something about this problem. So let's break down the CO2. Where is it coming from? This is a lot. We're going to start by breaking things down by economic sector first, and then we'll jump over here to this plot, but I'll give people a second just to glance at this slide. This is from the most recent report, up-to-date data. So this is broken down by country. Here's us. We're pretty big. Go us. This is one of the things that we don't want to be leading on, but we are anyway. Generally, it's the largest economies with the most people over here. Here's everywhere else combined. I don't know how many countries there are on Earth, like 180 something. And this is 1, 2, 3, 4, 5, make up slightly more than half. That's fun, he said sarcastically. But we're going to break it down by economic sector first. So where is this CO2 coming from? So we have electricity and heat. This is just energy use, I like to think about it. Here's land use, so agriculture, forestry are in the red section on here. Buildings, transportation sector is a big one people focus on. Industry, which is mostly just a special case of energy use, and then other. I'm not going to talk about other because it's just too complicated. So we're going to take these sectors one at a time, and we're going to start with the electricity and heat production sector of this thing. Okay. I know. You're welcome. Okay. This is an inside joke between Dr. Matthews and I. Okay. Anyway, so on average, just so you get your bearings, the average American household uses about 40-ish gigajoules of energy. That's just a unit of energy. Don't worry about it. I like joules. A lot of times when you're buying electricity or heat, they'll sell it in kilowatt hours. I hate that unit. It's annoying. Is everything okay? Oh, okay. No, but they looked concerned all of a sudden when I switched to this slide. Okay, good. Yeah. So Americans, we use a lot of energy. Other countries tend to use less energy per household, but this is going to be my benchmark for this. Generally, this energy can come from lots of different sources. I'm using energy, but really I'm talking about electricity for the most part here. So if we're generating our electricity from traditional coal power plants, that's going to emit approximately 12-ish tons of CO2 per 40 gigajoules of energy. So you, in your life, in 1 year, are effectively emitting 12 tons of CO2 into the atmosphere if you're getting 100% of your power from a coal plant. And so is every other household. Conveniently, we don't get all of our energy from coal plants, but we used to. In fact, about 23% currently of US electricity comes from coal plants. If it's a natural gas plant, that's what we're largely switching to in the US right now. Coal is definitely on the decline, which I realize is a politically hot topic in this region of the country, but it's just a fact. Natural gas does a lot better. This has to do with the chemistry of natural gas. Coal is basically just pure carbon. Natural gas has hydrogen in there also, so it emits a lot of water, which is also a greenhouse gas, but water has a tendency to like rain back down versus CO2 just stays up there. Anyway, so natural gas plants, they're emitting about 5 tons of CO2 per the amount of energy we use. This is why we're very pro-renewable energy, which releases 0 tons of CO2 per 40 gigajoules, which is not strictly speaking correct, because you do need to build the renewable energy infrastructure, and the construction of that is going to have emissions associated with it as well. But the upfront emissions versus the decades of running the plant, it's going to outweigh it. So renewable energy is the way to go. And that is the direction that the US is moving in as a whole. This was the most, sorry, I'm going on a tangent again. This was the most encouraging thing for me making this presentation, is because the last time I gave a presentation like this was during my Ph.D. dissertation, which was some number of 5 years ago, something like that. And the numbers were less favorable than this. We are moving in the correct direction. Are we moving fast enough? Probably not. But it is going in the right direction. The amount of renewable energy when I gave this presentation before was in the ballpark of 20% 5 years ago. So it's big, this change. So that's encouraging. You okay? Renewable energy for the win, fossil fuels, CO2. Great. All right, where else is it coming from? Let's look at the transportation sector. I really love these animations, they're so fun. Okay, so to get your bearings, transportation for most people is cars. Like we can talk about boats, planes, trains, all this stuff. But for us, mostly it's cars. So if we have a car, I've stolen Chevys for this slide. It doesn't really matter what the manufacturer of the car is, though. If your car gets about 30 miles per gallon, which seems like a reasonable fuel economy, especially on the freeway, you are emitting 340 pounds of CO2 per 500 miles driven. I just picked a nice round number for miles driven. This becomes complicated if we switch to electric vehicles. Why is it complicated? Because it depends on where your electricity is coming from. If your electricity is coming from coal, it's about the same emissions anyway. There's basically no gains at all switching to an electric car if you have coal energy. Conveniently, we're converting away from coal energy. So on natural gas energy, it's better because, again, natural gas doesn't emit as much for electricity usage. Renewables would be perfect, but we're not there yet, but we're making our way there. We get an increase by switching away from fossil fuel use again. Just so that we've covered all of our bases, they would walk 500 miles. Okay. And we're moving. Okay. One of the weird things about the okay, do we need to look at this again? For the young people in the audience, this was a band in the 80s, which was before I was alive. So I'm young with you too. Okay. Anyway. Sorry, I love rubbing it in so much. Okay. Anyway, a tricky thing about the transportation sector is, so currently we're switching to a lot of electric vehicles. Electric vehicles aren't even necessarily the best final, I don't want to say final solution because that sounds really bad, but final conclusion to our quest for the ideal energy. Because batteries are heavy. If you get into a battery-powered vehicle, something like, I don't even know what percent, huge percent of the weight of the vehicle is just battery pack. Like a Tesla, the whole floor of the car is built out of lithium-ion batteries. It's just like laptop batteries just stacked together in a grid of this car. They're heavy. If we're going to be serious about clean transportation, we need some kind of clean fuel to do that. So hear me out on this. So here we have a plot of, so this is what's called specific energy. This is how much energy you get per how heavy your energy source is. So if I take the amount of energy I can get out divided by how much it weighs. So this is in megajoules per kilogram. And on this axis up here, this is the energy density. So this is how much energy I get per how much space the thing takes up. All right, so if I have a big amount of space, it's going to have a low energy density. Okay, all of the dots on here are fuels. We've got some standard fuels. Gasoline is here, natural gas, propane like you use for your grill. Ammonia, hydrogen, these are proposed alternative fuels. I'm not going too far down this rabbit hole, but this is what I did my entire dissertation on, so we can go down that rabbit hole if you want to. Here's batteries. This is the state-of-the-art battery from Tesla that I'm reporting here, and this dot right here from their website made by their marketing department. So if anything, these are too favorable of numbers for lithium-ion battery. Batteries are heavy. They're not ideal for transportation fuels. They're great for some things. Like you're never going to power a personal electronic device with a gasoline engine. Forget it. That's stupid. You wouldn't do that. But in the same way, we're not going to fly a plane powered by batteries. You just can't do it. Like the thing would be so heavy, you wouldn't be able to put people and their luggage on the plane because the whole thing would be batteries. So we need some kind of research in the direction of alternative fuels and being able to extract energy without emitting carbon dioxide or other fossil fuels into the atmosphere. This is a good time to remind you, I'm in the stage of listing all of the problems. There are solutions coming later in the presentation. Okay, great. All right, look at another sector here. Agriculture, forestry, and other land use. But mostly I'm just going to talk about agriculture here. 2 big points on agriculture. A lot of people are very taken aback by how big that section of the pie is. I certainly was. Like, it's shocking how big that section of the pie is. And it comes from 2 causes. And the first one is livestock raising, specifically cattle. Sorry, Dr. Mathis, but he's a very small scale cattle rancher, so yeah. So the cows eat the grass, and this is where I'm losing, I don't fully understand a lot of the biology of this, but essentially at the end of the day, the cows, in the process of digesting the grass, burp up methane, which is also a greenhouse gas. It's actually a more potent greenhouse gas than carbon dioxide is. Like, it's bad. So this emissions contribution, these have all been converted to equivalent carbon dioxides once again. But notice cattle it's hard to estimate these numbers, but it's estimated to be about 3% of the total livestock population of the planet. We really like chicken. Chicken is delicious. But yeah, so here's cattle. 3% of the livestock on Earth, 62% of the greenhouse gas contribution of livestock raising comes from cattle. They take up a lot of space to graze, and they produce a lot of greenhouse gas just by existing. I mean, other livestock raising isn't innocent on this front, and by livestock raising, I, by extension, mean we, because if we didn't eat the livestock, then people wouldn't raise the livestock. So really, this is all our problem collectively. But yeah, livestock. Not obvious, but major, major, major source of CO2 emissions. The other big one, which I have a beef with this, but that's okay, is organic, large-scale organic farming, which has taken off recently, especially in the western part of the United States and the western part of Eurasia. That's right, I said Eurasia, fight me. So it seems great. First of all, I hate the word organic because all farming is organic by definition. Like, that's what organic means, carbon-based. I mean, come on. But anyway, sorry. We are deliberately doing less efficient agriculture if it's organic farming. Like, I understand like the moral sentiments about not wanting to have a good understanding of like where your like chain of chemicals going into your food is coming from. Sure, that's cool. Accountability is great. Most organic crops use crazy more resources, especially water, in their farming. So for instance, there was a study done in Denmark that I really liked that was talking specifically about reusable grocery store bags. How is that related to farming? Because they were comparing like one-use plastic bags, one-use paper bags, these cutie pies that we probably all have at least a few of, like the really thick, like waxy ones. These are actually also made out of plastic, so just so you know, but they're reusable. And cotton tote bags, and they calculated how many times you should actually have to reuse the plastic bag in order for it to offset just one use and throwing out the one-use plastic bag. And this was a complicated study. They looked at the entire life cycle of the bag, including like garbage pollution, that sort of thing. And they found about 50-ish times you would have to reuse this in order to make it worth it. 7,000 for organic cotton. It feels better for the planet, but the process of turning a plant and growing it and picking the cotton off that plant and processing the cotton, and sending it to a textile mill and making it into a bag and shipping those bags across the world for you to use has massive implications to the point where you are almost certainly better off just single use and throwing out the cheap plastic ones. So It's complicated. Basically, I pulled up this slide to be, it's complicated. This is such a depressing talk. I'm so sorry, guys. Normally I try and be fun. Okay. Let's talk about buildings. Because I think this is another interesting sector that people don't necessarily think about. And the next slide has a chemical equation on it. Oh, love it. Okay. Right? Okay. So it turns out manufacturing cement, as in like the stuff that we make sidewalks and roads and building foundations and all of this stuff out of, emits carbon dioxide. It just does. We're stuck with it. This is just what the chemical reaction does. Which is a major issue because there pretty much is no replacement for cement that we know of. That is, like, cement's about like one of the greatest like building material inventions humans have come up with ever. Like, if people in like ancient Rome were using it and we're still using it today, that should say something. But approximately over the lifetime of cement, and so this is actually for concrete, which is not 100% cement, it has other stuff in it too. It's about 1 pound of CO2 emitted per 10 pounds of concrete laid. So even just building any kind of new infrastructure, even if the new infrastructure is a nice new solar farm for clean energy, if there's cement in it, you're releasing CO2 into the atmosphere just for building it. So this is a relatively small section of the pie. This is probably one of the things that we should worry about tackling last on the list of things to tackle, but I'm just trying to get awareness for things you may not have thought of that are out there. Cool. So that's by economic sector. Where is this coming from by geographical region of the planet? So this is where we start. I don't want to go down the political rabbit hole either, but I suppose we can do that too in the Q&A. But I alluded to this earlier, solving climate change is a justice problem primarily because, as I say out here, 5 countries, 5, emit more than half of the greenhouse gases that go into our atmosphere every year. 5. The problem is that burning fossil fuels to emit the greenhouse gases is what propelled said 5 countries, including us, to the level of economic success that we have right now. Like, if you're looking at a standard of living in the short term for people, burning greenhouse gases is a good thing. If the oil industry disappeared tomorrow, if all gas stations closed, people would die in massive numbers because we need it for the infrastructure of our society. Like, the ambulances wouldn't run. The hospitals wouldn't have energy. Like just on a simple, it would be apocalyptic. This is how we built our society, is on greenhouse gases. So, we need to find solutions to this problem that do not hurt our standard of living, because otherwise no one would do them. Like, we don't want to fight the White Walkers. But also are cost-effective and robust enough to boost the standard of living in the other countries so that they aren't left behind in this race. We don't want to be exacerbating the gap between like the West and the rest, as they refer to it. We want everyone to be living in happy, clean earth together. I'm not a very good poet. Where's Jeremy? Not here. That's okay. Okay. So let's talk about clean energy. Let's start to turn the tide. Let's get hopeful. Let's get hopeful here. Okay. Global power sources. Where can we get clean energy from? I love this slide. All right. So here's the Earth. Dang, that's a pretty, I'm sorry. Okay. We're going to take the Earth and we're going to shrink it down to be about this size. And the surface area of this circle represents 18 terawatts. A watt is a joule, which is the amount of energy per second. So a watt is representing like the average consumption of energy over time. Okay. So we have 2 choices. We can use non-renewables or renewables. Right? That would be literally everything. Okay, so our non-renewables, these are your fossil fuels. These are things like coal, oil, and gas. And let's throw uranium on there too. Okay. And we could continue doing this foreseeably into the future and we would be fine. Like if you add the surface areas of these squares and that triangle together, they approximately equal the energy demands of the Earth. We could power all of the energy that the Earth uses with these fuels. But we don't want to because they emit greenhouse gases into the atmosphere. We've gone over that plenty. So let's talk about renewables. And there's a lot of discussion about all the different renewables that we can use. People talk about hydroelectric. Hydroelectric is great, but it's pretty much saturated. We have dammed up like every river that we possibly can. So this is done. So, but there's the cute little circle for it. People talk about tidal energy. Let's try and absorb the energy from the tides flowing back and forth. And you can do that, and you will get this much energy, which is not zero. So we can do this, especially if you live in a place like New Orleans and you already have levees in place anyway. Might as well have your levees generating energy for the Big Easy. Why not? Okay, great. Here's ocean wave energy. This is essentially like deep ocean version of tidal. The oceans are big, so this circle is bigger, but that's just not a good idea. We're not going to talk about that. Geothermal is awesome if you happen to live in a place where it's convenient, which means there's got to be some kind of volcanic, for lack of a better word, activity near-ish to the surface of the Earth. Like Iceland famously gets almost all of their energy from geothermal, and it's completely clean, and it's super robust, and it's great, and it's just not going to work in Ohio or most places on Earth. Geothermal involves like pulling energy out of like the warm part underground on Earth. It's fun. Anyway, here's biomass. So this is like the clean ethanol kind of stuff that you hear about. Let's grow our energy because that's pulling CO2 out of the atmosphere to grow it, and then when we burn it by conventional means, it puts the CO2 back. So this is a closed loop. So this is effectively carbon-free. The problem is that we calculated, and by we I mean these guys, calculated biomass using every single square acre of, acres are already square, every single acre of arable land on Earth and converted it just into biomass for fuel. And then what are we going to eat? So this is a bad idea also. Like, it works nicely in small areas. The main reason why it's so popular in the United States right now is because of, okay, I don't want to get political. Never mind, I'm not going to say that. It's okay. We like farming, let's put it that way. Oh. Wind is here, and solar is here. Except solar is not actually here. Solar is here. If you were to make, so this went off the screen. So this goes like, and then up into the second floor, and then back down. It's that thing, right? Yeah. 23,000 terawatts, and we need 18. The fun stat that people use is if we could which we could never do this, but if we could successfully harness all of the solar energy that hits the Earth in a day, that would be enough energy to power the entire Earth for a whole year. That's the scale we're talking about for solar energy. This is why people are psyched about solar. And you may have even noticed it taking off just in the past not that many years. The other cool thing about the renewable energies is they have finally gotten cheap enough to do this. This was the big caveat 5 years ago when I was doing my dissertation. This slide was a little bit different back then. This is a complicated graph. This is essentially showing how much it's going to cost per unit energy if you make your energy from all of these different methods. And forever, until we invested a lot of money and time into developing better wind and solar energy, these two bars were up here. And so it made no sense for any of these energy companies to build wind or solar because they could offer cheaper energy to their customers by continuing on this business as usual plan. Finally, we have made it to this level. Note, the error bars are very tall, so it depends on where you live. Solar energy is much cheaper in Arizona than it is in Maine. But we're still finally down onto grid parity, so that is great. Solar by itself is tricky, because you have this trifecta that you have to deal with, and it's extremely hard to hit all three of these criteria. You need it to be cheap enough that we can afford to build it. You need it to be robust enough that it lasts, and we need it to be efficient enough that it actually, works and gives us the energy that we need. So we need to hit all three of these at least a little bit. And there's two general approaches that people use for solar energy, and they are solar thermal energy, which is a more like traditional way, and solar photovoltaic energy, which is the cool way. I'm a little bit biased, but that's okay. So solar thermal, this is pretty well established methodology. So this is essentially, you take sunlight, you focus, it's like using a magnifying glass to light something on fire with the sun. That's basically what this is doing. You're taking solar energy, concentrating it into a certain little point, and then absorbing that heat and using it to boil water and turn a steam turbine, just like we almost always generate electricity, right? This method has a relatively low maximum efficiency. I have comparisons for efficiencies down here. So your coal plant is about 45% efficient in terms of theoretical yield of energy that comes in versus the amount you get out. Plant leaves are actually really terrible at converting energy, because most of the energy the plant gets from the sun, it has to spend fixing the components of the plant that get the energy from the sun. So photosynthesis is a very, it doesn't not work, is the term that the biologists like to use. I stole that from Dr. Hall. But it works just good enough that the plants are doing fine. It's good enough for them, but we don't see tree beard anywhere because they can't make that much energy. Tree beard being like the walking tree from Lord of the Rings. It's an old movie that came out before you were born. Okay, great. This is a big solar thermal plant in Morocco, by the way, which is relatively new. It's really cool. Anyway, so solar thermal I would call cheap and robust, but not especially efficient. It's not as good as the coal plant, and that the power companies go when it's not great. Photovoltaic, on the other hand, these are more popular in areas that are less warm, such as this one is in sunny Cleveland. Yeah, they built it on top of a trash hill. Delightful. Good use of trash hill, though. Higher efficiency. So this uses relatively complex chemistry that I happen to not want to talk about in this presentation right now, because it involves like bonds and orbitals and electron transfers and all sorts of fun stuff that I would love to chat about, but everyone will fall asleep. But clever chemistry and physics turns solar energy directly into electricity. More efficient, less cheap. So, yeah, that's fun. We're working on it. It's this business it's moving. We're already going in this direction. It's good. How about fuels, though? In the transportation sector, we cared about fuels. How are we going to make fuels? There are different directions on this front. The two leaders I put on this slide because it's like an inside joke in my field that these two guys are like neck and neck to win the Nobel Prize, and they can't stand each other, but they had the same Ph.D. advisor who thinks that, well, okay, he's a great guy. If you can ever meet this dude, he referred to them as, quote, a real piece of work, end quote. I love it. This is being recorded. I'm sorry, Dan. Okay, anyway. You didn't hear from me. Anyway, so there are solutions similar to like how this turns light directly into electricity. This turns light directly into fuels. So on this side, on the West Coast camp, they're turning light and water directly into hydrogen and oxygen. They're burning hydrogen backwards with the idea that you can then inject hydrogen into like a fuel cell or something like that, which we'll get to in a second. On the East Coast camp, instead of making a new fuel, hydrogen, he has a slightly less efficient system that it makes a more conventional fuel. This is isopropanol, which is just an alcohol. You could put this into like a normal engine and it would work, which is pretty cool. So those are solutions. I wanted to plug my own stuff on here too. I tried to mimic Dan Nocera's picture. You see the resemblance? Yeah, I tried. I don't have the beard, so it doesn't look as good. Anyway, I'm going a little bit of a different direction because I can't compete with Caltech and Harvard. Like, they literally have budgets in the tens of millions to spend on this stuff, and I have budgets in like the tens of dollars to spend on this stuff. So I'm working on like a smaller bite-size project. So in my lab, this is one of the two projects we're doing. We're working on, it's okay, Ron. I'm working on using solar energy to do chemical processes that are interesting. So I'm not making a fuel, but in this project specifically, we've got this material, and the idea is it will react with impurities in the water. So if you have like a wastewater supply, and it goes through a wastewater treatment plant, and there are chemicals, I know it's 4:30, I'm trying to go fast. There are chemicals that make it through the wastewater treatment plant and are in very small concentrations in our drinking water, and we want to get rid of these. Normally it's expensive and energy intensive to do that, so we're trying to work on a cheap, robust, sunlight method of doing this. So similar chemistry to the previous slide, but not making fuels. We can talk about this later too. I'm sorry, I need to go faster. Solutions in transportation. Probably the long-term answer, at least for cars, is fuel cells. I know people have been talking about fuel cells for decades, and they're always like, it's 1 decade away. It really is coming soon. When companies like these have production vehicles on the market, these are from their current websites. You can buy one of those cars today. Like most cars, it's probably back ordered by like 12 months or something like that. You don't actually buy a car today. That's a different story. These use hydrogen directly as their fuel, and they feel like you're in an electric car. It's basically the same idea as a battery-powered vehicle, except instead of putting electricity into it, you put hydrogen into it, and instead of burning the hydrogen, it systematically sucks the energy out of it using a fuel cell, which we can talk about in more detail. Should have gone faster at the beginning of the presentation. I'm sorry, Sister Diane. If you have somewhere to be at 4:30, you should go now because it's 4:35. Okay. Agricultural solutions. We've seen massive gains on this in the past couple of years too with fake beef. Oh dang, is the Impossible Burger good? If you haven't had one, you should try it. It's amazing. Alternatively, I'm not trying to advertise for this company, but the slogan actually makes sense. Like, if you can't get away from meat entirely, consider ordering the chicken sandwich instead of the burger if you're out at a restaurant, because some livestock is more friendly to the environment than others. They also have chickens at the Mathis estate, so I've just compensated. Cool. But I'm just one person. What can I do by myself? Good question. Let's talk about some solutions here. If you can afford it, we have reached the point of grid parity where it might finally actually be worth it to put solar panels on your roof. It is no longer just the crazy people in Southern California. If you actually do your research, make sure you have found a good, reliable company and a good, reliable contractor to do this, and you've negotiated with your power company to make sure that you can send your excess energy back onto the grid, this might be financially worth it, especially if the south side of your house is not the side facing the street, because then it doesn't hurt your curb appeal either. Champion. What else can we do? Vote for people who take climate change seriously. I'm not saying who those people necessarily are, but it can make a difference. If the people that that you want to vote for aren't taking climate change seriously, that's fine. Call them or send them an email, because it's 2021, and tell them to take climate change seriously because you care. If the government doesn't think that we care, then since they represent us, they won't do anything about it. Do not immediately sell your car and buy an electric car, because there are emissions associated with making a new car. So if your car is fine, don't get rid of it. Keep it for the lifetime of the car, and then consider buying an electric car, because the emissions of an electric car are going to wind up being better than the emissions of a gasoline car, especially if you're using it for just short distance commuting. A long trip in an electric car might be a little bit hazardous right now. So not hazardous, but boring while you wait for an hour for it to charge in middle of nowhere, wherever you were stuck on your trip. Yeah. Or, you know, if one of these options is feasible, do that. I hate walking, but we all need to do our part. Meatless Monday. Or we're Catholics. Meatless Friday. Yes. Solution. This is good. It's going to wind up being better on all. Still go out to eat. Support your local restaurants. Just order like the veggie burger instead of the hamburger. And you can still have a beer. And you can still have a beer. You can't still have a beer. Good? This is a quote from the IPCC report towards the end of the report that I wanted to tie up on. They say there's no going back from some of the changes in the climate system. Like, we're stuck. We're on the roller coaster is halfway up the hill already. We just have to see what happens at this point. However, some changes can be slowed and others can be stopped if we take action now by slowing and limiting warming. All right, let's do the Q&A. Go. Yeah. Attack, go.
I have two questions.
Yes.
One, what about the yellow cylinder?
What about the yellow
The
cylinder?
garbage.
All right, so that depends on what's in the garbage. She's making a reference to a board game that I blatantly stole images from. Don't worry about it. So she's asking about burning garbage as a form of energy. So the emissions are probably similar to burning. So obviously if there's like toxic things in the garbage, it's a bad idea. If it's regular garbage, the emissions are going to be similar to probably more like gasoline or oil or something like that. That's most of what our garbage is anyway, is like paper and plastic stuff. So the emissions are going to be on par with that. It gets really complicated really fast when you're looking at the overall environmental picture. One topic I didn't really talk about on here is carbon capture, because that's not extremely well developed at this point, but the idea being if we can put some kind of device on the top of a smokestack that can suck all of the CO2 out of the smokestack and then we can just bury it in the ground somewhere, that coupled with burning garbage is a really exciting solution, because then we get rid of all of our garbage, we get electricity, and we're not putting greenhouse gases into the atmosphere.
And what about insects for protein?
Sorry, insects for protein?
As a protein source.
So I didn't have data on them, but supposedly that's the most sustainable animal protein, is what I've heard. Okay. Yeah. I mean, I don't have data on insect farming globally. Oh, you do?
I'll send you an article.
Gorgeous. Okay. This was controversial. Let's go. Let's go. Assault. Assault with questions. Rock and roll.
As far as carbon in the ocean, carbon in the atmosphere,
Yeah.
those numbers just what we calculated from our production.
What do you mean? What numbers? The plot? Let's go way back. Way back.
One thing in mind for me was we'll keep staying inside the atmosphere. What about the solar cycles? What are we going to do about that in the solar cycle? And like undersea volcanoes or placement.
Oh, yeah. So solar cycles is most, okay, I'm sorry, this is like way back in the slides. I should have used the little scrolly thing instead of hit the arrow a million times. One of these days I'll get back to the slide. Where's the CO2 slide? Come on, there, nope. Yes. This is the magnitude of solar cycles and tectonic plates and all that kind of stuff. Not tectonic plates, but thermal cycling. So this is a nice smooth line in the model. It won't be a smooth line. It'll be like a bumpy line that goes on that path. What the Earth does naturally by that sort of thing is on the order of like plus or minus 100 ppm. A more complicated tangent on that front is so CO2, more CO2 in the atmosphere causes it to dissolve in the water more, but warmer planet causes it to dissolve in the water less. So there's this complicated back and forth differential equation kind of nonsense that you have to solve. So that's a big unknown question mark because we don't have data for what the oceans will behave like when they're 5-10 degrees warmer than what they've been almost forever. So we don't know.
But you don't remember that when IFL went off in Iceland, it shut down half a year, and they calculated that it quite possibly will leave more carbon than all the industrial revolutions.
Sure, yeah. What's weird about like volcanic activity is most of what it spews up is just ash and that sort of thing. And that usually leads to a noticeable decrease in temperature because it's not the greenhouse effect. It doesn't, because the greenhouse effect, the light comes in and the heat doesn't go out. With volcanic ash, the light doesn't come in as much either. And these models actually account for that. If you read what they're saying, they say like, so the greenhouse gas contribution to warming is bigger than that and is partially counteracted by cooling from other aerosols in the atmosphere. This is not to say that we should just dump aerosol into our atmosphere, but volcanoes just happen. So, yeah. So,
it seems that there's a silver lining to the pandemic, and that is that so many people are working from home. Has someone figured the savings in commuting, transportation costs, and office space costs?
probably, but I don't know the number. But I'm going to go with almost certainly yes. What is really interesting that happened during the pandemic, especially, and I think it was India, they noticed a noticeable increase in air quality because of the lack of commuters and doing things. And this is not to say we should just shut off our economy. That's not a good idea long term for like public common good. But yes, that's a thing. No, I don't know what the numbers are. Bear in mind that if we're all working with like the internet and data centers, those are causing emissions as well because they use a lot of electricity. Probably not as much as we're emitting by driving to and from work, but these problems are multifaceted and complicated. Sorry, I basically answered your question with I don't know. Claire.
Seeing as an alternative energy gases, I didn't see much for nuclear. But I know that's a problem.
Yeah, so the problem with nuclear is no one wants to do it. Nuclear is actually like general public. They freak out if you're going to build a nuclear plant in your backyard. Nuclear is interesting because we could do nuclear. And if you do an assessment of like the risk analysis of like lifetime of like coal coming out of the ground all the way through electricity generation versus a nuclear plant and the probability of there being a meltdown, it's actually significantly safer also for just everyone. The problem I think with nuclear is people are just so afraid of like the 1 or 2 times ever that something massive has gone wrong. It's the same reason why people are more afraid of flying than they are driving a car, even though your chances of getting into a serious car accident are stupidly higher than the chances of you getting in a plane accident. But it just feels more dangerous being in a plane. I think that's the main reason why people are afraid of nuclear. I'm speculating. But we, in principle, could do nuclear. There just isn't a good social pressure to go that direction.
What exactly, I'm assuming then that nuclear is more efficient and cost efficient. What now about it makes it so
So first of all, nuclear is a subset of multiple different technologies. I quoted traditional uranium fission, which is like old school nuclear. We're into better nuclear technology right now. Thorium looks really promising as a nuclear fuel. At the end of the day, nuclear is just pulling heat out of a lump of radioactive metal and using that to boil water and spin a turbine and all that fun stuff. So in principle, it's just as efficient as any other method, except it has no emissions. Big caveats of nuclear: they're expensive to build and maintain. You need highly educated people to run them. I mean, you need literal nuclear scientists. What are you going to do with the waste? Another problem with nuclear materials. They wind up, no one wants these anywhere. Like the U.S. has done some hilariously dumb things with nuclear waste in the past. If you want to Google that. Such as like, oh, we'll just throw it in the ocean, it'll be fun. Yeah, that's the thing. There's also nuclear fusion coming at some point on the horizon. That's another thing that's always been, oh, it's just 20 years in the future. It's been just 20 years in the future since the 60s. Someday it will happen, and that's the ultimate answer. But for right now, wind and solar looks like a great thing to do now that people more or less understand and can get behind. And the now part of it, I think, is more important than getting the best long-term solution right now. Did I hit all of your questions? Okay, sorry, I rambled there.
We could probably go on all night.
Oh, yeah.
I think some people are anxious and so on. I just want to really thank you then for that very thoughtful timing. And why don't more people take action? We've heard this many, many times, but we don't all take action.
I mean, I don't do as much as I should either. I get up here and I'm a hypocrite. I drive a gasoline vehicle, I eat steak, yeah.
It was a wonderful song.
Thank you. Thanks for having me.